about this in some of the imaging groups, is how do we know what we're looking at is anywhere near the truth? Because obviously we didn't have a version of an image of the black hole before. So how do we know this looks like what it actually looks like?
So that is a really, really deep question. A question about like, how do we know the image is correct? We're taking an image of something that's never been seen before using a telescope that's never been used or calibrated before. And although that's no longer true for this image, but so now we actually have something we can compare it to the previous image it got. But this is a more generic question of how do we know with this kind of answer, what can we do to really to really make sure that we're getting something that we believe to be correct? And that is such a fantastic question, and it's really multifaceted. So there's multiple approaches that we've done to validate and ensure the correctness and validity of the image. And there has been some, discussion online, as there always is. It's a black hole image. How can we know it's correct? Is there, consensus in the community, stuff like that? How does the community trust our results? And so this is what we basically put forth to convince people. So first and fundamentally, we have the data are worked on by separate teams of people that each bring their own assumptions and tools to the problem. So, for example, there are different imaging algorithms that you can use to reproduce these images. And we have 4 teams of people that use 4 imaging algorithms that are basically grouped into 2 types. And they each bring their own expertise, assumptions, prior knowledge about the object, and make their own independent image blindly. We then give these images to a computer algorithm that gauges for us how similar they are, and it tells us first what percentage alike they are. And if the percentage is really high off the bat, then we know that we're, even with our different assumptions and our different algorithms, we're getting the same answer out of the data that tells us the data are resistant to our prior assumptions and our tools, our humanity. And that's a really, really good check. And for both of these images, these 4 separate teams came together and produced basically the same results. There were some minor differences, but the salient features were there in all the images. A ring of about 40 microarcsecond diameter with a brightness asymmetry to the south. And so that right off the bat is one easy check.
Yeah, it should be made obvious. I don't know how clear it was. Very nice explanation. But those 4 teams do not talk to each other. They're so-called blind imaging. And so, for instance, the group you were in, you worked together as a mini collaboration, 13, 15 people. But you didn't talk about your results or your methods or your priors, the input into these theoretical models. You didn't discuss those with the other 3 groups. That's right, isn't it?
That's correct. Yes. And we were extremely strict about this. So I actually was one of the organizers for the workshop in 2018, where we produced the first image of a black hole. And we had people literally hold up in separate rooms, and we would put film on any windows or openings so that nobody can see inside. And because this was such a big event, there were documentary film crews and stuff filming us, a la the penguins from Penguins of Madagascar. And so one of the documentary film crews attempted to subvert the rules we had put in place to try to restrict any communication or preliminary images from getting out. And they tried pressing up their cameras to a hole we had left in one of the windows. And even though they were just trying to do it because they were trying to get an image for an exciting sneak peek behind the scenes preview or whatever, it was so critical that the image not get leaked to each other, to the separate teams, that we kicked the documentary crew out after that. So just for that single act, that was how strict we were about not letting any communication pass between the teams. And no team saw each other's images until after we had run it through this computerized comparison to assess how similar the images were to each other.
That's great. Has that documentary crew returned from their stint at the South Pole Telescope now as punishment?
from their imprisonment in the Phantom Zone.
That's right.
No, they're still out there going, I'll find him.
I'll find you. I'll be back. Super important, this, Joseph, really important point, and I'm really glad you made a big showing of that, because I think that's one of the things that would, again, be destructive to the scientific method, is to minimize as much as possible the human input, the biases, the preconceived ideas we have sometimes when building our algorithms and doing our data analysis. So I think having those 4 separate teams really did, at least as well as we were able to do with the data in hand and the algorithms we had available to us and those we developed, that we were able to minimize those biases, minimize cross-contamination between teams. And also, yourself, if you ask a question of somebody and but you sort of give them a hint along the way, they're probably going to find the answer that you want them to find. And that is completely unscientific.
Yes. And that's a serious problem that we had too, because we kind of knew what we wanted to get. Not what we wanted to get, but we kind of knew what we expected from the physics. We had simulations.
That's right. Yeah, but I think working to scientists try to avoid this at all costs, is we don't work toward an answer that we already have in mind. We work toward the answer. And sometimes it's disappointing. Sometimes it's not either the answer you want or you prefer, or it doesn't look good for a flashy press release. But that fundamental honesty to say, we're going to work toward what the data give us, what our fundamental training has given us in mathematics and physics and astronomy. And you get what you get and you don't get upset. And so I think that separating those 4 teams was really a fundamental part of the scientific method that we followed quite rigorously.
It was, but it wasn't the only way we validated the images. So part of the problem is, while the 4 teams on the face of it sounds like really good already, and it is, let's consider a simple example where you have 2 possible but distinct images that could fit the data, which is not uncommon in VLBI.
Absolutely.
We don't know if that's going to be the case going in, but let's say you have 2 distinct images. Let's say there's just if you give any random imaging team the data, there's like a 50-50 shot they'll get one image or the other. Even with 4 completely independent imaging teams, there's still a 5 to 10% chance that we'd all accidentally get the same image, whereas there was another one hidden in the data. So we had to address this very specifically, and we actually targeted the bias that we all knew we had, which is that we knew from simulations that if there was a black hole there, we'd expect it to be something like this, where there's this ring and there's a depression in the center. And that by itself is not problematic, that we had a good prediction, but we have to make sure we avoided it. And so what we were worried about was that our imaging algorithms, we would either subconsciously or consciously influence them to taking whatever image we found and putting a hole in the middle. And so we designed a suite of tests that everybody had to go through first in order to make sure that the imaging algorithms that we created avoided these kinds of pitfalls. And so, actually, sorry, I don't mean to flick around, but this is exactly what we're talking about. So here we have the different imaging teams, and these are also some modeling as well. But here are 3 separate imaging algorithms: Smiley, EHT imaging, and DiffMap, on the different days of data. And what you can see is that they all produce the same structure in the images. This ring with the exact same size and this brightness distribution in the exact same direction across all imaging bands, across all frequency bands, across all imaging algorithms and modeling, which is a completely different beast from imaging. We get the same result, and this is what we're talking about by that validation.
Nice.
So, regarding addressing our specific biases, this is one of the ways we do it. So we design these things called synthetic data tests. We create ground truth images that we know the correct answer to. So here's a crescent, here's a ring, here's a binary source, and here's a disk. And you might ask, why did we pick these? And the answer is they all produce visibilities that look pretty similar to the real data. And so just by looking at the data, which is the yellow data points in this figure over here, just by looking at the data where it has this clear peak and then fall and then bump, that Bessel function, that behavior is called a Bessel function, and it immediately tells us that it probably has to look like one of these 4 images. And so by creating these 4 synthetic data tests and then simulating how an observation would look with all the intricacies and noise and array configuration of the real EHT, we can take this data without saying this is a crescent, ring, double, disk. We can take this data without telling anybody what it is and just give them to the imaging teams and see what they recover. And if they were subconsciously influenced to put a hole in the middle, for example, to reproduce a shadow, they wouldn't know that the disk did not have a hole in it, and so their reconstructions would have a hole. And so what we see is that this is not the case. For each of the objects, we're able to extremely accurately recover what the original source looked like. And you can see there's smaller features that we don't trust, that they don't appear in the images. And that's why when we look back at the images, we don't say, for example, oh, we trust this tiny little knot that appears, but we trust the overall features, which is that, for example, this crescent has a bias towards the south. And in the images, we see a bias towards the south, a bias towards the south, a bias towards the south. This ring has a uniform distribution. And you can see it has a uniform distribution here, here, here. There are these little knots and knobs, but they're evenly distributed. And same with the binary and the disk. So this is a hugely important approach we have, these synthetic data tests for testing our algorithms in a scenario where we know the correct answer. And that's a very, very important validation.
Yes, I think that's what I was getting at earlier about the ground truth. How do we know what we're reproducing is truly representative of the physical conditions around that black hole? And these two plots explain this perfectly. Actually, you did a good job there. That's very, very nice.
So that's with the, I'm very happy to say this is still not the only way we test this. So one of the other things that we do is we have this thing called a calibrator source. So as we're imaging M87, as we're the telescopes are pointing at M87, every few minutes they turn and they point at another object that we actually know what it should look like because other people have imaged it just at longer wavelengths. And so when we take our imaging algorithms, theoretically, because the array configuration, everything is exactly the same, the imaging algorithms and the settings we find and that we use and the assumptions we make should apply equally to the science target and its calibrator. So when we point at the science target and the calibrator, if we use the same imaging algorithm to reconstruct both, the calibrator should give us the image we know to be correct based on other observing campaigns at longer wavelengths. And so in this case, M87's calibrator was a quasar called 3C279, which we've actually published research on in the past. And we found that when we pointed at M87, when we pointed at 3C279, we get the same images that everybody else in the community gets, just with higher resolution, basically. And so that tells us that, okay, the imaging algorithms are working to reproduce something else that other people have seen. When we take the exact same algorithms with the same settings, the same everything, and apply it to M87, we get this new image. That gives us a huge boost of trust. So it's, and honestly, I could keep going and going and going with the ways we validate, but this is an incredibly, incredibly robust result. And this is just how we validate our results internally. We're not even getting to the point where independent teams have come in, taken our data after we published, and reproduced the results for themselves and seen and gotten the same thing with minor differences. And those differences have then gone on to drive the field as a whole as to how we, what's wrong with our algorithms and stuff like that. But everybody gets the ring with the brightness asymmetry to the south.
Yeah, absolutely. Now, that's a really good point. And in fact, you and I discussed this earlier this morning before we came on air, is that the consensus among the community that they are able to reproduce our images, at least to reasonably good fidelity with the same data set, is really, really a good indication that we are at least eliminating the biases in ourselves and in our processes as best we can. Now, does every single person in the community reproduce what we reproduce? No. Does every single group agree with us? Not necessarily, but the vast majority do. And so that really gives us reassurance, while acknowledging there could still be some issues to iron out, and we have improvements to make, of course, that's the nature of science. The fact that so many groups around the world are able to reproduce our images, are able to follow a similar scientific method and get almost the same results that we do within the errors, at least, means that if there are one or two groups that aren't able to reproduce our images or don't get the same results, they are probably either doing something perhaps not as well as we are, or their imaging algorithms aren't quite as developed as ours. But I think it really does show that we were very rigorous in the beginning in eliminating our biases, is setting ground truths and understanding our algorithms as best we were able to.
I love the way you put that. And it really is like, it cannot be overstated. The vast, like overwhelming majority of the community has tried to reproduce our results in a number of different ways, and has come to the same conclusion. And the disputes are often more about interpretation than it's largely undisputed in the community. Like the vast majority of people in the community agree we found a ring with a brightness asymmetry. The papers that come out disputing it are excellent, and they actually make us think deeper about the physics behind it. Like, is what we're seeing exactly as we interpret it? Is it the shadow of the black hole? What specifically does that mean? And you can get really specific. Like we said before, these are photons that are orbiting around the black hole. It turns out each of the photons, as they orbit around the black hole and complete a higher and higher number of orbits, leads to a slightly different image on that all a slightly different image each time that all add up to produce our image. And that's a really, really interesting subtlety. And so that's the kind of stuff where like that's where the disputes really lie, is what precisely are we seeing in the context of general relativity and this object. But it really is across the board. It's one of the, I think you could argue it's one of the most robust results and like reproduced results just in the history of astronomy. Like I don't know in terms of the ratio of like how little was known prior to how trusted the results are now, given that we had an instrument that's never been used before, never been calibrated on an object that had never been seen at the spatial resolution. The way the level of trust the community had in our results, due to the literally hundreds of pages of validation that we published, and the transparency we had, right? We didn't just publish the data for other people to work on. We published our scripts, our full imaging algorithms. You can go home right now, and maybe we should have an Astraveo tutorial. You can go home right now and run these scripts and produce these images yourself and play with the settings and see how it affects the outcome. And so it's just such a robust result. I love working in this collaboration.
No, see, that's phenomenal. I do like that aspect of it. In fact, I think you mentioned a really important point, is that we were scientifically honest. We said, here are the data, here are our algorithms, and here's how we operate them. You go and to other scientific groups, go ahead and see if you can reproduce what we did. See if you can do it better. See if you get some anomalies that we didn't notice. And again, as you rightly said, for the vast majority of groups around the world, they were able to reproduce our images really quite well. And make the same physical inferences about black hole size and spin and magnetic field and those really important physical characteristics that do define the cosmological interpretation of black holes. So I like the way you put that. That was good. That was very good.
It's such, and I love what you added there too. It's really, you're right. It's really an important point.
Yeah, one thing that used to bug me actually is that I would go to scientific talks or conferences and people would present a graph or some plot, and it would have these beautiful data, and the correlation between the data was wonderful, and you'd show some plot, some model on top of the data to interpret it. And I'd always think, where are the bad data? Because we all get bad data. It could be that the instrument, the instrument wasn't doing what it's supposed to, the telescope pointing couldn't have been quite right, the humidity jumped up in the atmosphere. There's all kinds of reasons, right? Or you could have just made a mistake, which holistically we must do as scientists. But these plots look so perfect and pristine. So I would ask the question of the author or the presenter and say, why are your data so close to your model? Where are the pathological data? And they would reply that they removed them from the plot. And I say, well, I think that's scientifically dishonest. You should show your poorest data as well as your best data. Because if you have lots and lots of poor data, it shows that there's a problem in the experiment or your analysis of the data. And so I made a firm sort of commitment to myself as a young scientist, sort of your age scientist, and said, I'm going to publish all my data, warts and all, the bad ones, the good ones. Can you explain the bad data? Yes, that's good. It was cloudy, or the telescope operator fell asleep, or you spilled coffee on the computer. It was all kinds of silly reasons. But you show your poor data as well, and most of them will always be excluded with things like large error bars, which yourself, mathematical fits will essentially ignore. But showing those poor data is very, very important for scientific honesty, and it sort of really enhances your reputation as a scientist.
And honestly, that's how I know you personally, and that's how you conduct yourself as a scientist. And it's had a big impact on me as a budding astrophysicist that has inspired the way I want to approach my work as well, directly inspired by you.
Thank you, my friend.
And I did hear there was a great quote in the HG collaboration at one point when we were discussing, how much of the bad data to include or not, and the overwhelming consensus was there's no such thing as bad data, only bad scientists. And it's a little harsh, but like the idea is like, there's no such thing as bad data. If you have bad data, then you have procedures and models that correct for it. If you're just throwing out data that is making your life more difficult, then you're not really following the scientific method there and treating your data the way it should be.
Yeah, right. I think that's one. Actually, I'm really glad you said that. I think that's one of the points I was trying to make, but not quite as eloquently as you. Is that when one as a scientist starts including data because you're sort of afraid of the interpretation or how your colleagues will feel about you, or you think it'll be a good data point to sort of prove your point. Again, that working to a result is absolutely what we do not try to do. We always try to see what the data tell us, and we try to get that ground truth. If you're expecting 1 star plus 2 stars to equal 3 stars, you will work toward that. Whereas if you're working toward what does 1 star plus 2 stars give us, then that's a whole different scientific experiment. And it's fundamental that we don't do the first case, we actually do the latter. We work toward what we think is scientifically best. Because if you start impinging or imparting, that's probably a better word, your own humanity on the data sets, it makes them irreproducible when you go to another group or another astronomer or another algorithm. Because if you cherry pick your data, a different person could cherry pick different data and they'll end up with different results. So culling your data is really a very, very poor scientific practice.
I totally agree. I think you summed it up perfectly.
Very nice. Thank you.